Okay, so today we have around 20 questions, and these 20 questions are regarding the change in tandem chapter, which is a subsection of Unit 1. Now, starting off with question number 1, a student starts to drive to school from home in a straight line and quickly realizes that they forgot their backpack. The student stops the car and then drives back to their starting position at home. So this is home, and we have a student who's basically driving from home all the way to school. Now, let's just continue on with the question. For this context, which of the following graphs could model the velocity v in miles per hour of the car as a function of time t in hours? And this is a really, really important note, is that assume driving away from home involves positive velocity. So moving away from home is a positive velocity, and moving back home would be a negative velocity. So if we want to graph this, we have this student who's going away from home, and then he realizes at this point that they forgot their backpack. Well, they're not gonna basically they're not gonna like press on the brake and do a full brake and then just stop, right? If you're pressing on the brake, it's gonna slowly come to an end, right? The car will slowly stop. And this is when the student stops. Now they wanna go back home, which means a negative velocity. Now let's have a look at the answer choices and see which answer makes the most sense. And a negative velocity, well, let's just first look at the answer choices. We have option A, which tells us that a student is driving away from home. They reach a point where they remember that they forgot their backpack. Then they slowly start to stop the car, and now they're moving back home with a negative velocity. At this point, they need to let me just reach that point one more time. Okay, at this point, they need to basically press on the brake, but it's not going to come to a full brake. The car is slowly going to come to a stop, and that's when they stop at home and basically grab their backpack. So it is in fact option A. Why isn't it option B? Because with B, it doesn't start with a negative velocity. The student's actually moving away from home, which is a positive velocity. It is not C because the student needs to go back home. And it is also not D because the student does start with a positive velocity. So the correct answer is in fact option A. Now moving on to question number 2, the graph of the function f is shown. On which of the following intervals is the graph of f of f? Why did I say f of f? Well, f of x, there is no x, it's just the graph of f concave down. Concave down is a function that has concavity that's basically facing downwards. So the graph would be facing towards the x-axis. Now let's have a look at the answer choices. From negative infinity up to negative 2. Well, this is negative 2, and you can in fact tell that the graph is facing downwards, which is concave down. And that is true. Let's have a look at the other answer choices though. What about negative infinity to negative 4? That is also concavity downwards. Union 0 to infinity, well, from 0 to infinity, as you can tell, it's facing upwards, so that's not the case. Now, when we change colors, that might actually help me trace answers a bit more. Okay, B's out. What about D? Negative 2 to infinity, well, negative 2 to infinity has a concavity which is upwards, so that's out as well. What about negative 4 to 0? Well, this one is interesting. From negative 4 to 0, the point of inflection, I would say, is at negative 2. So from negative 4 to negative 2, it was in fact facing downwards, but from negative 2 to 0, it was then facing upwards. And remember, we just want concave down, so that is not the case. The correct answer would be option A. Moving on to question number 3, the table describes rates of change of a function f for selected intervals of x. The function f is defined for x greater than or equal to 0, and it's also less than or equal to 4. On which of the following intervals is the graph of f concave down? Now, for a function to be concave down, just remember this, that rate of change is simply decreasing. Now, if rate of change is decreasing, then it's concave down. If rate of change is increasing, it's concave up. Now, please don't mix these two up. It doesn't have the function, let's say the function is increasing, right? F of x is increasing. This has nothing to do with whether the function is concave up or concave down. A function may be increasing, but it's concave down. This is concave down, right? And a function may be increasing and it's concave up. How do you determine whether a function is concave up or concave down? That relies on the rate of change. If a rate of change is increasing, then it's simply concave up. If a rate of change is decreasing, then it's concave down. Now let's have a look at the answer choices, which is concave down, which means we're searching for a rate of change that is decreasing. It's not from 0 to 1. Well, with 1 to 2, it would be positive constant. The word constant means that the rate of change is a straight line. And this is y equal to mx plus b, because m is not changing, right? But in this case, that's not what we're searching for. We're searching for a decreasing rate of change, which would result in a concavity, which is downwards, which is 2 to 3, which is option C. Okay, moving on to question number 4. A toy car travels around a circular track as shown in the figure. As the toy car travels around the track, its distance from the wall can be modeled by a graph where the y-axis represents the distance between the car and the wall, and the x-axis represents the time. So let's have a look. And before we graph this, let's have a look at the starting point. So this is where the car starts, which means it's touching the wall, which also means that there's a distance of 0 between the car and the wall, right? That's the starting point, so there is no distance between the wall and the toy car. And time in this case also equals to 0, and y equals to 0, so this is our starting point. As the car moves on to this point, let's say, I'm going to give it an engine, there you go. Once it moves up to this point, the distance between the car and the wall will obviously increase, right? So let me show you what the distance looks like. Let's change colors. This is the wall and this is the car. So this is the y distance, right? Now let's say our car is now at this point. This is our car, this is its engine. Now what's the distance between the wall and the car? It's gonna be this distance, right? And then you have the fourth point and so on and so on. You can do as many points as you want, but that's not what we're doing in this case. What we're trying to do is just figure out the graph and move on to the next question. Well, the maximum point would be this, so the maximum distance between the wall and the toy car would be at this point, right? And then what's gonna happen is simply gonna start to decrease and up till it reaches back to the starting point. Am I correct? Yes or no? I am, supposedly. We're gonna have to go back to this point, and we're just gonna do another loop and another loop and another loop, right? Well, how many times? Which of the following graphs model this relationship as the car goes around the track 3 times without stopping? So it's gonna have to do this 3 times. Now, this must be replicated 3 times. Now let's have a look at the answer choices. Well, it's most likely equal to option A, 1, 2, and 3. Well, why isn't it B? Because the distance will never be negative. When is the car when does the car have a negative distance with the wall? If I want to measure distance, do I ever measure it as negative? Let's say I bring a measure tape and I want to take the measure of any object. Is there a negative measurement? The measure tape starts at 0, which means there is no negative, right? So in this case, anything negative would be out. This is quite different related to velocity. Velocity might have a negative distance. In this case, it does have a negative distance when it goes back home. Because remember, it's displacement over time, not distance over time. Now, going back to this question, distance can never be negative. What else do we have? We also have we have option C, which is always increasing for some reason. Well, the toy car is never just moving away from the wall. It's always coming back to it. It's always coming back at the starting point. So that is not the case as well. Well, a good answer choice would be option D. So let's say you went with option D, and that would be the second best answer choice, I would say. And why isn't it D? Because we're dealing with a circular track. At some point, the car will not have, the speed of the car is not constant along the circular track. It's going to have to speed up at some point and then slow down at another point. And that does affect the graph. So that's why it's not like a constant graph, constant rate. So it's option A, and that's it. Okay, moving on to the next question. Question number 5, the graph of the function f is given for -3 to 6. Which of the following statements about the rate of change of f over the interval 2 to 6 is true? Well, just by looking at it, before I look at the answer choices, from 2 to 6, the graph has a concavity that's facing downwards, which means that the rate of change is in fact decreasing, so it's option D, and that is it. So that's it for this one. Okay, moving on to question number 6. The graph of the function f is shown. Over which of the following intervals is f increasing? Well, it is increasing from -6 to -4. And what about the second part of option A? From 2 to 5. So yeah, that's it. It's basically option A. Let's just prove the other options incorrect. From -6 to 0, well, it was increasing, then it went on to a constant rate, which is not the case. So B's out. -4 to 2, -4 to 2, constant, then moves downwards, not the case. And then we have 0 to 2, which is basically downwards, right? 0 to 2, there you go. So this one is out as well. Let me just erase this. Okay, so it's option A. Moving on to question number 7. This one is very simple if you know how to graph it. Well, since you can use Desmos on the test, well, feel free to graph it, and actually you must graph it so you don't mess up. And yeah, let's see what the question's all about. We have a ball which is thrown through an open window to the ground below. The height of the ball in meters at time t seconds after it is thrown can be modeled by the function h, given by h of t equals to the following. Yeah, and which of the following describes the height of the ball above the ground? So this is our function. Now what I'm going to do is I'm going to graph this on Desmos on my phone. If you have a phone next to you, or if you're on, if you could just open Desmos on any device, it doesn't really matter. Just graph it. We have -4.9x squared plus 4.4x plus 15.24. Okay, so I graphed it. And once you graph it, what I want from you is to press on the maximum point. So it does look like this. And if you just press on the parabola, it's going to give you the coordinates. Now, the maximum point is called the vertex. which does have coordinates of 0.44 and 16.22. So when x equals to 0.44 seconds, y equals to 16.22 meters, right? So it's 16.22 meters above the ground, 0.44 seconds after it's being thrown. And that is the maximum point, right? Why? Because A is negative. When A is negative, the parabola is facing downwards, which means the vertex is considered the maximum point. In this case, remember, the standard form is ax squared plus bx plus c. We have negative 4.9x squared plus 4.4t plus 15.24, right? A is negative, it's facing downwards, so the maximum point is the vertex. And what's the case? So let's have a look at option A. The ball begins at its maximum height. That is not the case. No, it does not begin at the maximum height. The maximum height is actually 16.22, and it's not 15.240. So option A is out. So as option B, it mentions the exact same phrase. What about C? After leaving the window, the height of the ball increases to its maximum height of 16.228. This is in fact correct. Then the height of the ball decreases until it reaches the ground, 1.82 seconds. So let me just mark the point where it reaches the ground, which is this one, right? And that is when y equals to 0. We just need to find the x coordinate. Now, by looking at the graph, just by pressing on the problem one more time, y equals to 0 when x equals to 2.26. So I'm basically looking at the coordinates of this point, 2.2, oops, massive mistake. Okay, 2.260, there you go. And that is in fact option D, which is the case. So it reaches maximum height at the following and reaches the ground at the following, which is the correct answer. Moving on to question number 8, the table gives characteristics of the rates of change of the function f on different intervals. Which of the following is true about f on the interval 3 to 4? Well, if rate of change is positive and decreasing, so what does this tell us? It tells us that the rate of change is positive and decreasing. In this case, a decreasing rate of change means that the concavity is downwards. And if f of x is positive, then what does that mean? That means f is increasing with a concavity that is downwards. So that would be option A. Rate of change is positive, so it's basically moving upwards. The concavity is, well, it's decreasing, so the concavity is downwards. Make sense? So in this case, it would be option A. Now moving on to question number 9. We have water which is poured into an empty vase at a constant rate. A graph not shown models the depth of the water in the vase over time. The graph can be described as follows. The graph is always increasing. So the graph is always increasing. It could be increasing like this, or it could be increasing like this, right? The first portion of the graph is clearly concave up. The first portion is clearly concave up. And so it starts like this. And the next portion of the graph has a fairly steady and steep increase. So then the next portion has a fairly and steady steep increase. Which of the following vases is appropriate for the context described by the graph? Now, if it has a concavity that is upwards, means that it would take more time for the rate to pick up, right? So let me show you what I mean. So if I were to draw a straight line, let's say this point, in this case y equals to, let's say, 1, okay? This has a rate of change which equals to 0. Now as we move on to this point, y equals to, let's say, 2x. Now rate of change equals to 2, right? As I move on to this point, y equals to 4x, rate of change equals to 4. And this is basically the speed at which the vase is basically filling up. Now, if you look at the graphs, it would make sense if we go with option B, because it does take time for the vase to fill up at this point. Then it slowly starts to catch up, where it speeds up, and then this last portion is basically a steady constant. Now, why isn't it option A? Because we only have 2 portions going on, as you can tell, this portion and this portion. However, with option A, we have 3 cases, 1, 2, and 3. And that is definitely not the case, so option A is incorrect. What about C? Well, what about this part? They did not mention 1, 2, and 3, right? And this is not true. And what about D? Well, D isn't correct because if its concavity is upwards, it means as it's going upwards, this will start to slim in, right? So if it looked like this, that would have been correct. Like it's starting to slim in. There is no actually bumps to it, just like this. Which is definitely the case with option B. Because as it moves upwards, it's gonna have to slim in for this to have an increased rate. And D is not the case, so it's option B. Okay, moving on to this one. The figure shows a sphere that can expand. As it expands, the volume inside the sphere and the radius of the sphere both increase. In particular, the radius increases at a decreasing rate with respect to the volume. So let's read this one more time. The radius increases at a decreasing rate with respect to the volume. And okay, showing which of the following graphs could depict this situation where volume cubic centimeters is the independent variable and radius in centimeters is the dependent variable? So we have radius, which is y, and volume, which is x. And the question is, radius increases at a decreasing rate. So let me show you 2 graphs where the function is increasing. This is a function increasing, and this is also an increasing function. But this function is increasing at a decreasing rate, correct? And this function would be increasing at an increasing rate. Remember, both functions, I'm going to write this down, both functions are increasing. It's not as if one is increasing and the other is decreasing. No, both are increasing. But one is increasing at a decreasing rate, which means as we move further, it's going to be increasing, but at a rate basically that's decreasing. But with the second function, it's increasing at an increasing rate. Now, so it's definitely this function. Let's just graph it. It's going to look like this. Let's have a look at our answers. It would be option B. Increasing at a decreasing rate. Concavity is downwards, and that's it. D is decreasing, and A is also decreasing, and C is in fact increasing, but at an increasing rate. So always remember this. Whenever you hear the word increasing rate, it means that the function has a concavity that is upwards. Disregard the fact whether it's decreasing or increasing. You see option A, this function is decreasing. It is decreasing, right? But it's decreasing at an increasing rate. Now, what about this one? This function is decreasing, but it's decreasing at a decreasing rate. So always remember those two. Now, let's move on to the next question. This is question number 10, question number 11. Okay, at time t equals 0, water begins pouring into an empty container at a constant rate. The water pours into the container until it is full. The situation is modeled by the given graph, where time in seconds is the independent variable and the depth of the water in the container in centimeters is the dependent variable. So we need to understand this graph first. We have 1, 2, 3 cases going on. Well, the container is molded into 3 different stages, I would say. So the first stage and the last stage would probably have the same rate. If I would take a line at this point and a line at this point, they do have the same rate. And halfway, I would say it's a faster one. So it's going to be slim through the middle and more thicker towards the bottom and top. Probably like this. Not the exact same shape, but that's what I'm guessing. Because now you may ask, why is it slimmer towards the middle and thicker towards the top? Because this would have a rate of change of, let's say, y equal to 7x. It's more facing upwards, right? So let's say this line. And these two lines, 1 and 2, have more rates that are slow, so this would be like y equal to 2x. So y equal to 7x. So with y equal to 7x, the water the container is filled at a faster rate, correct? So it's to be more slim compared to the... I'm a bit sleepy today. Compared to the bottom and top parts of this container. Yeah, which is definitely option B. Is it? It is, yeah. Well, it has to be slim towards the middle, which is not the case with C. Slim towards the middle, not the case with D. And this is just one blob, one shape, which is obviously not the case. We have 3 different shapes going on. It's not just a constant. Okay, this is a good question, actually. It's a good answer choice. So this would just be like a constant straight line. That's it. It's not changing. The rate is not changing. Okay, moving on to question number 12. What is this about? No, my bad. Here it is. Okay, for t between 0 and 16, the rate at which customers arrive at a certain restaurant, is it? Yes. On a given day is modeled by the function r, where r of t is measured in customers per hour and t is measured in hours since the restaurant opened. The function r is the function is increasing for the following and it's decreasing for the following. The function n models the total number of customers who arrived at the restaurant since it opened up to time t. Now remember what this represents. The rate at which customers arrive at a restaurant on a given day is modeled by the function r. So r of t represents the rate. When they say that t is between 0 and 4 and 8 and 12, they tell you that it's increasing. What does this mean? This means that the concavity is upwards. When it's between 4 and 8, 12 and 16, the concavity is downwards. They also mention that the function models the total number, the function n, which is a totally different function, models the total number of customers who have arrived at the restaurant since it opened up to time t. Now, as we move on with time, the total number of customers will just basically increase. The number of customers, the total number is never decreasing, right? Even if a customer leaves. So let's say we have 5 customers who enter the restaurant, right? 5 customers enter the restaurant and then they leave. Well, I just wrote down on a piece of paper that 5 entered, right? That's the total number of customers who entered the restaurant today. And then 5 enter at another period of time. So let's say this is at 10 a.m. This is at 11 a.m. Another 5 customers entered. Now I'm at 10 customers, right? 10 customers entered today. Then at 12:15 entered it. Disregard the fact whether customers are leaving. You're just writing down how many customers are entering that restaurant since it opened. So the function NFT is always increasing, but it may increase at an increasing rate, or it may increase at a decreasing rate. Now let's have a look at the remaining questions. We do have, I'm sorry, not remaining questions, remaining answer choices. So yeah, we just need to search for where its concavity is upwards from 0 to 4. And it would be option D, from 0 to 4, concavity is upwards. From 8 to 12, concavity is upwards, which is the case as well. This is downwards and this is downwards, and that's it. The function is always increasing. Okay, let's have a look at question number 13. The figure shows a swimming pool filled with water, and a pump is used to remove water from the pool until the pool is empty. When the pump is running, the rate at which the volume of water in the pool decreases is constant. Okay, so what are they doing? In this case, they're filling up the swimming pool. And yeah, they did mention a really important point, is that the rate at which the volume of water in the pool, it's decreasing at some point. During the first 2 hours, the pump works slower than usual due to a broken piece. So during the first 2 hours, it's moving slower than usual. Then the pump stops working for a certain period of time. Did they mention? No, they did not mention how many hours it stopped working. Then they mentioned the broken piece is replaced, and then the pump works at its usual rate until the pool is completely emptied out of water. I'm sorry, they're removing water. Just realized that. The entire process of emptying the pool takes 6 hours. So at 6 hours, the pool should be empty, so the function should be at this point. Now, assuming this is time and this is y, which it represents the depth of water as we remove it from the pool. Okay. Which of the following graphs could depict the situation where time in hours is the independent variable and the volume of water in the pool in gallons is the dependent variable? Okay, dependent means y, independent means x, right? Always remember that y, let's say y equals 2x plus 3. Y is dependent because it depends on x. Y depends on x. Y depends on x. So y is the dependent variable and x is the independent variable. Now let's have a look at option A. Option A, the pool is emptied at 10 hours, which is not the case. With option B, it's emptied at 6 hours, which could be the case. At option C, it's emptied at 6 hours, which could be the case. And same with D, which could be the case as well. So we were able to cancel out only option A. Now, what about, let's have a look at this part. Okay. They mentioned during the first 2 hours, the pump works slower than usual due to a broken piece. So the first part should be slower than the second part. Now, that is definitely not the case with option C, because this part and this part are the exact same rate, and this would be when it's no longer working, right? So C's out. And what about option D? Well, with option D, it is moving at a slower rate than this one, that is true. Let's say y equals to negative 2x. This is y equal to negative 5x. This one is emptying the pool at a faster rate. And that is correct, but don't forget the second part. Wait, let me see option B. Well, that is the exact same thing with B, slower. So let's say y equals to negative 2x, and this is y equal to negative 5x. That doesn't really help us choose between B and D. But how do we choose between B and D? We actually continue on with the question. They mentioned that the pump stops working, the broken piece is replaced, and the pump works at its usual rate until the pool is completely emptied out of water. Okay, so during the first 2 hours, I'm sorry I forgot to mention that. So during the first 2 hours, okay, let me just erase this. During the first 2 hours, the pump works slower than usual due to a broken piece. So it's moving slower than usual for only the first 2 hours, which is option B. However, with option D, it's moving slower than usual for the first 4 hours, which is obviously not the case. So it is in fact option B, which is the correct answer.